Hey guys, Mr. Betts here. I want to talk a little bit about Maclaurin series and specifically how we can derive the Maclaurin series for the sine of x function, which we could really use this process for any function. You are expected to know the Maclaurin series for sine of x, cosine of x, e to the x, which can all be derived using this process. You're also expected to know the Maclaurin series for 1 over 1 minus x, but there's a trick with geometric series and the sum of a geometric series that you can use to get that one. So anyway, without further ado, let's get into this. So if we want a Maclaurin series, remember that the nth term in a Maclaurin series is going to be x to the nth power. Let's start with this. Sorry. The nth derivative for a Maclaurin series is centered at x equals 0 divided by n factorial times x to the n. Now, if it was just a generic Taylor series, this would be x minus a here, and this would be an a in here. But since it's centered at x equals 0 for a Maclaurin series, this is what we've got. So what I'm going to do is I'm just going to start taking derivatives of f of x, and as you would expect with sine, and this also happens with cosine, and much more quickly with e to the x, we're going to run into a pattern. So we've got f of x is sine of x. Got f prime of x is cosine of x. The second derivative is the opposite of sine of x. The third derivative is the opposite of cosine of x. And then when we get to the fourth derivative, we are back to sine of x. So the fifth derivative is going to be cosine of x. The sixth derivative is going to be negative sine of x, and so on. Then we want to evaluate each one of these at x equals 0. So f of 0 is 0. F prime of 0, cosine of 0 is 1. Second derivative at 0 is 0 because sine of 0 is 0. Third derivative at 0 is negative 1. The fourth derivative at 0 is 0. And so you may notice here that every other one of these is 0. And then every other of the remaining ones is going to be a positive 1 and then a negative 1. So the fifth derivative at 0 is negative 1. The seventh derivative at 0, fifth derivative is positive 1. The seventh derivative at 0 is going to be negative 1, and so on. So this pattern here is going to allow us to establish a pattern for the Maclaurin series for sine of x. So now that we have those, let's go ahead and just start building it. So I'm going to say sine of x is equal to, so I'm going to put equal because we're going to make this an infinite series. And so at least within the interval of convergence, these two functions are going to be equal to each other. So the first term is going to be the zeroth derivative evaluated at 0, which is 0. And anytime we have a 0, that's just going to go away. So then the first non-zero term we're going to have is going to come from the first derivative. So that's when n equals 1. We're going to have 1 over 1 factorial times x to the first power. So it's going to be 1x. Then the n equals 2 term is going to be 0. I'm going to ignore that. The n equals 3 term we're going to have, so it's going to be negative 1 over 3 factorial times x to the third power. Okay, again, I'm plugging into that equation there. Fourth derivative, that drops out because it's 0. So then we're going to have a fifth degree term. So it's going to be 1 over 5 factorial times x to the fifth. The sixth degree term drops out because that's going to be 0. Seventh degree term is going to be negative 1 over 7 factorial times x to the seventh, and so on. And at this point, I think we've established a pattern that if I rewrite this here, it's pretty easy to see. So first non-zero term is going to be x, then it's going to be minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. Now with that and so on, I want to include what's called the general term. So basically something I can plug into a formula and get any term I want. So since it's alternating positive and negative, we're going to have a -1 to a power. I'm going to try the nth power. If the nth power doesn't work, I'm not going to have enough room here, so I'm going to do this underneath. If the nth power doesn't work, then I'll modify that a little bit. The exponent is going to be some number to the 2n, say +1. So if we take any integer number, 2 times that +1 is going to give us these odd exponents, and then this is going to be over 2n plus 1 factorial. Now, just to check to see if I did this appropriately, I'm going to just try plugging something in. So to get the first term here, that's going to be an x to the first power. So it's actually going to be when n is 0. And if n is 0, we get -1 to the 0 power, which is positive, x to the first power over 1 factorial. So that gives us the first one. When n is 1, then we get -1 to the first power times x to the, 2 times 1 plus 1. So that's x to the third over 3 factorial. So that works. So that pattern allows us to get this general term here. And so this right here, and I know it's kind of sloppy, is the Maclaurin series for sine of x. So now that we know what the Maclaurin series for sine of x is, let's take a look at the interval of convergence. So essentially what we're looking for is what x values can we plug in to that Maclaurin series so that the sine function is equal to the Maclaurin series. So for the interval of convergence, I'm going to use the ratio test. And for the ratio test, first let me write the series here. So sine of x is equal to the sum from n equals 0 to infinity of -1 to the n. And then it was x to the 2n plus 1 over 2n plus 1 factorial. So again, that's what we got here for our general term. So I want to take this series and see what x values I can plug in so that that series converges. And if it converges, it's going to converge to the value of sine of x. So for example, if it converges for, say, 1, I can plug 1 in for x here, and I can plug 1 in for x here, and these two series are going to be equal to each other, or those two values are going to be equal. So to do the ratio test, we're first going to evaluate that limit. So r is the limit as n approaches infinity. And I'm just going to write out the formula for it first, essentially. So we're taking the n plus first term divided by the nth term. Remember, the ratio test is essentially looking at whether the series behaves like a geometric series, and if it does, we can use essentially the conditions of the geometric series test to see if it converges. So the n plus first term, so we got absolute value. I'm going to do n plus first term as -1 to the n plus 1 times x to the 2 quantity n plus 1 over 2 quantity n plus 1 factorial. And then we're going to, instead of dividing by the nth term, we're going to multiply by the reciprocal of the nth term. So it's going to be 2n plus 1 factorial over x. I'm going to throw that -1 in there. I do want to point out at this point that the -1 to the nth power, since we are in an absolute value, is just going to go away. So I'm going to start by getting rid of that. Okay, so the -1 to the nth power, the n plus first power, those don't matter because we're inside of an absolute value. We're going to have some canceling here. So this is x to the 2n plus 3. And so with those x's, we're going to have 2 more x's up here than we have down here. So that means that with canceling, I'm just going to cross them both off, we're going to end up with an x squared there. And then with the factorials, this is 2n plus 3 factorial, which is, I'm going to rewrite that another way, that is 2n plus 3 times 2n plus 2, just one less than that, times 2n plus 1, times 2n, times 2n minus 1, but everything from here on is 2n plus 1 factorial. And by writing it like that, we can see that the 2n plus 1 factorial and 2n plus 1 factorial cancel each other out. So we can rewrite now. So this is equal to, so the x squared we can take out front. Remember that we have absolute values here, but if we square anything, it's going to end up positive, or if x is 0, then it's going to be 0, and the absolute values are not needed. So I can pull that x squared out, and I don't need the absolute values anymore. I could leave them if I wanted to. And then we have the limit as n approaches infinity. So all that's left out of all of that is this stuff down here in the denominator. So 1 over 2n plus 3 times 2n plus 2. And so as n gets really big, the denominator is going to get really big there, which means that it's going to go to 0. So we get x squared times 0. And regardless of what x is, that's just going to be 0. So keep in mind that if we're plugging in an x value, that's going to be a finite x value. So even if x is, say, like 1,000,000, once n gets to be bigger than about 1,000,000, now the ratios are getting smaller and smaller and approaching 0. So the behavior of this limit, it's going to take a while. It's not going to happen until we get to really big n values if x is a big number, but this limit does approach 0. And based on the ratio test, since 0 is, I should probably write this part in, that is less than 1, that's the condition for the ratio test, that means that the series is going to converge no matter what x is, so the interval of convergence is going to be all real numbers, or negative infinity to infinity. This is actually a really important result, because what this means is no matter what x value I plug in to the Maclaurin series here, I'm going to get a value equal to the sine of that same number. Now, I also want to point out that this infinity here is important. It may take, depending on what x is, it may take like millions and millions of terms for this Maclaurin series to even become a decent approximation. So I'm not saying that this is a good Maclaurin series to approximate the sine of 30. However, if we were to plug 30 in for x and use infinitely many terms, sine of 30 and this series with 30 in there for x will be the same value.